Hi dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 224. In this lecture, we will try to understand geometrical interpretation of principal component analysis. Before understanding this geometrical interpretation, let me recall my lecture number 223, in which we discussed about why learn PCA. We discussed this topic, isn't it? Just let me spend few minutes time on this particular topic. We humans have the power to visualize only 2D, 3D data using scatter plots. I already discussed what is scatter plots in data visualization techniques, isn't it? Again, 4D, 5D, 6D data using pairwise plots. Simply I can say using pair plots. In real scenarios or in real situations, we mostly have data set more than 10 dimensions. In such case, it is difficult to visualize by using pairwise plots. The solution here is the solution to visualize higher dimensional lies within dimensionality reduction. Isn't it? What you have to do? Dimensionality reduction. That is the solution. As you have more dimensions, you have to reduce dimensions so that you can visualize data, isn't it? One of the simplest and fundamental technique of dimensionality reduction is PCA. Who is helpful? Your principal component analysis is PCA is useful, or principal component analysis is useful to reduce the dimensions. I already discussed, if you have a data point xi belongs to Rd, it is in D. If it is d-dimensional data, what you have to do? You have d dimensions. You have to reduce this d dimensions into d dash dimensions, isn't it? D dash dimensions, isn't it? Where, what is the condition here? Where your d dash is less than d. That must be the condition. I can say usually this d can be 2D or 3D. Why? Because visualizing data in 2D or 3D may be a little bit simple, isn't it? Let's take a simple data set of 2 dimensions to understand geometrical interpretation of PCA. For easy interpretation, why am I considering a simple data set with only 2 dimensions? Because for easy interpretation, I am considering 2-dimensional data. The findings on converting, my intention is here, I must convert 2D to 1D, isn't it? It is something like d-dimensional data set. This is d dash dimensional data set. Anyway, d dash is less than d. Of course, you may ask me, 2-dimensional data is easy to visualize. It's true. That's what I'm saying. For easy interpretation, just I'm considering this case, converting 2D to 2D into 1D, isn't it? The findings on converting 2D to 1D will work perfectly for higher dimensions too, isn't it? By using linear algebra, once if it is valid from 2D to 1D, you can extend this discussion for other dimensions too. Suppose we have data set of students which comprises of 2 features as height let me say like this. I have students with two features. What are the features? I have first feature. Feature 1 is, I can say, age of the students, which represent of two features as height and age of the students. Here two features are, let me say, let's the data set have first feature. Feature 1 is age of the students and feature 2 is height of the students. Let me say there are n data points, 1, 2, so on n. How many features does this data set is having? Two features. Feature 1 is age of the students and feature 2 is height of the, this is age. First one is age, your second one is height of the students. How many data points are there? There are n data points. How many columns? There are 2 columns. So that I can say it is n by 2 matrix, n by 2 data matrix. Here 2 features, isn't it? I can say it is 2D. This can be, even this can be expressed. This particular data matrix can be represented in the form of a graph, is it not? This is the graph. You can understand this graph. Normally in the classroom, what happens in the classroom, the spread of age. What is feature 1? Just go back and see what is feature 1. Feature 1 is age, feature 2 is height. Therefore, let me write my feature 1, this one is age, and my feature 2, this one is on y-axis. I am taking feature 2, that is height. Normally in the classroom, the spread of age will be less. That you must understand. The spread of age, how much spread, how much variance, this is the spread, isn't it? This is a spread, I can say. This is the spread, this is the variance, I can say. This is the information, I can say, isn't it? This is the information I can. In a classroom, normally in a classroom, the spread of age will be less, very less. Spread of age will be less compared to heights of the student. This spread or this variance, this is information of age, whereas this one, what is this spread? This spread, this height, this is spread for what? Spread for heights of the students, heights of the students in a classroom. As we are seeing in the graph, the spread of feature 1 is very low. Just see this just see this width and this width. This width is very low, isn't it? Which width is very low? On age. I can say, as we are seeing in the graph, the spread of feature 1, that is age, is very low. Here the spread means variance. I can say spread means variance, or even I can say information. The information contained by feature 1 is very low. Information of feature 1. Information of feature 1 is less than information of feature 2, isn't it? Feature 2. Otherwise, I can say spread of age, spread of information, or spread or variance. Spread of age is less than spread of heights, isn't it? Spread of heights of the students. The information contained by feature 1, that is age, is very low as compared to feature 2. If forced to represent the data set in one dimensions, feature 1 can be removed easily. Why? Because this age, feature 1, can be removed easily as the spread is very low. Just see, the spread is very low. What does actually PCA performs? That one must understand. What does actually PCA performs? PCA performs. We were discussing it is useful for reducing dimensionality. PCA preserves, or otherwise I will write. Let me write PCA preserves. PCA preserves the feature. Preserves the feature with maximal variance. With maximal variance, otherwise I can say spread, or I can say information. In the graph, it is bit easy to visualize the dimension which holds maximum information, maximum spread, which dimension is holding maximum spread or maximum information. That is feature 2, that is heights of the students, isn't it? In that case, what I can do, this just see, this is two-dimensional data set. In that two-dimensional data set, I have feature 1. Feature 1 is age and feature 2 is heights, isn't it? There is less spread on age. Therefore, you can remove this feature 1, isn't it? You can preserve feature 2. This to n by 2 matrix is converted into n by 1 matrix. This is two-dimensional data set is transformed into one-dimensional data set. Which one is doing all these things? This PCA is useful to transform this two-dimensional data to one-dimensional data. This can holds good for higher dimensional data set. Is also, as feature 1 has got less information, less variance, less spread. This PCA removes feature 1 and it preserves feature 2. Therefore, your n by 2 data matrix will be converted into n by 1 data matrix. That is, two-dimensional data set is converted into one-dimensional data set. That is dimensionality reduction. If you consider one more simple example, one more little bit tricky example, let me say I have data something like this. I have data like this. I have data, let me assume like this. I have data like this. In similar manner, I have data points. Let me assume this is a case. This is a case. What is a spread on x-axis? This is starting, this is ending. You have this much of spread on x-axis. What is spread on y-axis? You have spread this much of spread on y-axis. Is it not starting on y-axis? Is it not ending? This much spread you have on y-axis. This much spread you have on x-axis. Means data uniformly distributed. I can say this is the case. This is the case, data uniformly distributed, uniformly distributed along both dimensions, along both axes, along both dimensions. Now, which one, let me say this is feature 1. Let me say this is feature 2. Which feature can I drop? It is difficult. It's not that easy, as you have spread on both the features. But whereas in previous case, just see this case, what happens? Here you have less spread. It's simple case. You have spread only on feature 2. You don't have spread on feature 1. You have very small spread on feature 1. Therefore, you are able to remove that feature 1 and you are preserving feature 2. But here this case is a little bit different. You have spread on both the axes. In the graph, the data is spread on both the dimensions. Then in that case, now what I have to do? I must rotate the axis. How can I do it? Rotate the axis. What I have to do? Rotate the axis. How can I rotate? Rotate the axis. Where you have spread in this direction. You have spread in this direction, so that you must rotate the axis. Let me say rotate the axis to find the dimension, otherwise I can say feature, dimension or feature which contains maximum information, isn't it? Which contains, I must rotate the axis, isn't it? Just in this direction you have variance. This is, therefore I must rotate this F1 with this much angle, isn't it? This F1 will become F1 dash. With that angle, again, I must also rotate with the same angle F2, so that you will get a perpendicular line. If I rotate your F2 with the same angle, why? Because originally F1 and F2 is perpendicular. I am rotating F1 as F1 dash. isn't it? With some angle theta. With that same angle, if I rotate F2, this you will get F2 dash. F2 dash is, you must understand, your F1 dash must be perpendicular to F2 dash, isn't it? You must understand as rotation, as rotation will not change, as rotation will not change the actual data. That you must understand. Rotation will not change the actual data, isn't it? Rotation will not change actual data. It will change position only, isn't it? It will change only relative position. It will change only relative position. That one must understand. It will change only relative position, isn't it? That's what rotation, only relative position of what? Position of what? Position of data points, isn't it? Position of data points. Steps, it's simple. Just see this diagram, you can understand this one, isn't it? Just it's simple diagram. This is original feature F1. I am rotating with some angle theta, so that it's a direction in which you have maximum variance. Just I am rotating F1. Again, that F1 will become F1 dash. I must draw a perpendicular to this one. That is F2. F2 dash, this I can say. Why? Because you are rotating F2 with that amount of angle. It's such that your F1 dash, this condition important, your F1 dash must be perpendicular to F2 dash. Just see here, you have same spread. You have spread along x-axis. You have spread along y-axis also. You have spread. Therefore, I cannot discard any one of them. In which case, what am I doing? I am rotating F1 along this particular line, along which line this spread is high. With the same angle, I am rotating F2, so that F1 becomes, this is F1 dash and F2 dash must be perpendicular to each other. Now, what you have to do? Steps, now what I have to do? What is the spread along F2? You have very less spread along F2. Therefore, you can drop F2, isn't it? Let me write steps otherwise. Above, steps have been done. I will write steps otherwise. Let me write steps. Yes. Steps have been done on the above mentioned data set to obtain F1 dash, comma, F2 dash. First, what I have to do? Step number 1, rotation of axis. First point is rotation of axis. Rotation of axis to find F1 dash and F2 dash. To find F1 dash and F2 dash, where F1 dash represents maximum variance. That you must understand. Where F1 dash represents maximum variance. Max variance. That is important. Max variance, isn't it? Now, if you observe this one, drop F2 dash. What is the reason? Drop F2 dash as spread. What's the reason? As spread on F2 dash is very, very less than spread on F1 dash. Just see, this spread on F2 dash is very, very less than spread on F2 dash. Therefore, I am dropping F2 dash. After that, what you have to do? I must project all data points. Project all data points. Project all data points. Project all data points or data set points xi. Project all these xi on F1 dash. On F1 dash, on which variance is very, very high. Isn't it? This is on which variance is very, very high. This projection, I already discussed this projection in lecture number 212. I request you to refer this lecture number 212. In that lecture, I promised you to derive perpendicular distance of a point from the plane. I will derive maybe in next lecture or in coming 1 or 2 lectures. Maybe in next lecture I will try to derive this simple derivation, isn't it? I can successfully convert 2D data into 1D data with the help of projections. Just go through this lecture. In my next lecture, I will discuss geometric interpretation of mathematical, this is geometric interpretation, isn't it? We will try to understand mathematics behind principal component analysis, but I will also discuss this perpendicular distance of a point from the plane. Just go through this lecture. If you have any difficulty, just keep a comment. Thank you very much.